In this final video where we talk about the introduction to inverse trigonometric functions, we kind of pull out all the stops and we take a look at trigonometric inverses of non-similar trigonometric functions. In the previous video, the inverse always matched the inside function, but that doesn't happen in this case. We are also going to look at functions of inverses that are not on the unit circle, which is going to cause us to bust out our Pythagorean theorem and also learn a little bit more about Pythagorean triples and proper simplification of radicals. It would be extremely good for you to have your full unit circle that we made back in Unit 1. We'll be referring to this quite a bit. So without further ado, we are going to get to this Unit 2 end of the unit. So let us first off analyze what we're going to do here. We are going to take a look at when the inverse tangent, it's looking for a location now. So I want the location where the inverse tangent is the same numeric value as the cotangent of 2 pi over 3. So let's go look at 2 pi over 3. If I look at 2 pi over 3 and I check the cotangent value, it's negative square root of 3 over 3. Alright, so now I can go back to my sheet here and I can actually do a little bit of changing of this problem. So now it's the inverse tangent of negative square root of 3 over 3. Okay? And what's great about this is this kind of leans back to the second video in this series where a problem like this is asking, okay, where in the first or fourth quadrant is the tangent of inverse tangent negative square root of 3 over 3? So this is great because we have this unit circle and we can look in that fourth quadrant and we can say, oh, hey, check it out. That tangent is negative square root of 3 over 3 at 11 pi over 6. Now, before you get happy and you might write down 11 pi over 6, you can't leave your answer that way. Now you might be thinking, why? And the reason why is because 11 pi over 6 is not technically within the fourth quadrant. Now it is in the fourth quadrant, but to get to 11 pi over 6, you have to go whoop to get there. All right, and that a terminal side, yes, it's in the fourth quadrant, but you had to get outside of the first and fourth quadrant to get there. So the proper way to write the answer is negative pi over 6, which is going whoop like that right to the terminal side of the angle that you're looking for. So you gotta always be careful about this here. All right, now let's do this problem. I guarantee this one will be a little bit easier. Okay, the inverse cosine of the tangent of negative pi over 4. All right, so first of all, let's go to negative pi over 4. Negative pi over 4 is not up here in the first quadrant. Negative pi over 4 is in the fourth quadrant. And negative pi over 4 at the tangent value is negative 1. So what I now have, and I can rewrite the problem as the inverse cosine at the value of negative 1. So this problem is asking me, okay, where in the first or second quadrant is the inverse cosine equal to negative 1? And it exists way at the end of the second quadrant, and it's a place we can get to because we can go from the first quadrant to the second quadrant inclusively, which includes 0 degrees and 180 degrees. So this is problem 22, and that's right. Now, if we look at problem 23, there is no way that 13 pi over 6 is within the first or fourth quadrant. So let's just figure this out and maybe get a better perspective than this super big theta. So let's remember that 2 pi is the same thing as 12 pi over 6. Because if you multiply the top by 6 and bottom by 6, you get an equivalent fraction of 2 pi. And 12 pi over 6 plus just pi over 6, that's going to be equal to 13 pi over 6. Thanks to the periodic rule states that we can rewrite 13 pi over 6 as a multiple of 2 pi and its remainder. So this problem now becomes the inverse sine of the cosine of pi over 6. Now, lucky for us, cosine of pi over 6 is in the first quadrant. And if I go to look at my first quadrant and I see, oh, okay, there's pi over 6, and cosine at pi over 6 is square root of 3 over 2. Square root of 3 over 2. Great. So now what I have is I have the inverse sine of square root of 3 over 2. So inverses look for locations. So this inverse sine is saying, okay, where in the first or fourth quadrant is the sine value equal to square root of 3 over 2? And it can't be square root of 3, it can't be pi over 6, it's pi over 3. See, here's my sine at square root of 3 over 2. So my answer in this problem is pi over 6. So for my final problem, I'm going to tackle it one of two ways. So I'm going to give you method number 1. Okay, here's method number 1. I'm going to rewrite that negative 11 pi over 4 and find out where it is. So let me remind ourselves that negative 2 pi is the same thing as negative 8 pi over 4. Negative 8 pi over 4. That's exactly as negative 2 pi. If I multiply top and bottom by 4, that's what I get. Minus 3 pi over 4 gives me negative 11 pi over 4. Okay? So, according to the periodic rule, we can write any fraction as 360 degrees minus that fraction, or 2 pi, and that'll get us to the same answer. So this is going to be the inverse cosine of the sine value at negative 3 pi over 4. Okay. Now what I'm going to do is I'm going to look up negative 3 pi over 4 on my unit circle. Okay? I'm going to look up negative 3 pi over 4 on my unit circle. Now, 3 pi over 4 going in the counterclockwise direction would take me to this 135 degrees. That would be from 0 degrees, but I'm not going positive 3 pi over 4. I'm actually going negative 3 pi over 4. And negative 3 pi over 4 takes me down here. And so the negative 3 pi over 4, which is here, the sine value is negative square root of 2 over 2. Okay, so now I'm going to continue writing this here. This is going to be the inverse cosine at negative square root of 2 over 2. So what this problem is asking me is okay, where is the inverse cosine in the first or second quadrant equal to negative square root of 2 over 2? And your answer is 3 pi over 4. See, check out my cosine value there, negative square root of 2 over 2. So my answer is 3 pi over 4. All right, now that's one way you could have done the problem. Here's another way you could have done the problem. And I'm going to branch this off in this direction right here. So I basically got to this direction in black, but instead of going clockwise and then figuring everything out from there, I'm going to use my odd-even functions and say, okay, you see how I have a negative sign? I can rewrite that as the negative sign of the positive, like so. Okay? I can do that. I can just take the negative and move it in front of the sign. This is true for all trigonometric equations except for cosine and secant. For cosine and secant, the negative would just go away. You actually have homework problems in this section that remind you of these odd-even functions. So it is good to remember that any kind of function that isn't cosine or secant, you can take the negative and move it to the front. If it's cosine or secant, you just drop the negative because the rotation doesn't matter, because the rotations don't matter with respect to x. Yes, I did cover this in a previous video. You'd have to really hunt to find that. So now what I'm going to do is I'm going to look up the sine at square root of 3 over 4, and that sine value at square root of 3 over 4 happens to be square root of 2 over 2. So the problem then becomes the cosine inverse of the square root of 2 over 2. But you see how I have that negative in front? Well, there I have that negative. And this takes me to the same conclusion as this did, because I'm asking for when is the inverse cosine in the first and second quadrant equal to negative square root of 2 over 2? And the answer is 3 pi over 4. Okay, so you can do it either way, but the reason why I want to highlight this method is because it covers our odd-even functions, which is going to be asked in this section of homework. So, to move on to the final 3 problems of this section in this chapter, you'll note that I did change the ordering of these problems. So if you have an earlier version of these worksheets that I gave to students, 25 and 26 are in a different place. And also I changed 26 to be cotangent instead of tangent. So make these changes. This makes 26 a lot more, what's the word I'm looking for? Test level? College level? All right, well, let's first of all handle this situation. This is the situation where the inverse tangent is 4/3. This is not on your unit circle. Like, this inverse tangent is looking for a location, and 4/3 is not on the unit circle, but we can still handle this by drawing a triangle, because the tangent exists either in the first or fourth quadrant. The inverse lives here, first or fourth. And since everything's positive, then this is going to be positive like so. I'm going to put in my theta right there, and what this means is that my answer is going to be the sine of theta. So I'm turning this into a picture with this relationship represented as theta. Now, if I can find all 3 sides of this triangle, then I just use my SOHCAHTOA of the opposite over hypotenuse, and that will give me the answer for the whole problem. So let's get started. Tangent, according to SOHCAHTOA, is opposite over adjacent in relationship to theta created with a right angle from a reference angle in the first quadrant. We don't know how big the triangle is, but we do know it's this orientation. So this would be opposite over adjacent in relationship to theta. Now what we are going to use is we're going to use our Pythagorean theorem. A squared plus b squared equals c squared. But in this case, it's going to be x squared plus y squared is equal to hypotenuse squared. This allows us to look at the relationships between x and y, and also the hypotenuse h. So x is equal to 3 quantity squared, y is equal to 4 quantity squared, and I usually put parentheses around these in case they're negative, and the hypotenuse is just the hypotenuse squared. So now we have 9 plus 16 equals the hypotenuse squared. 25 is equal to the hypotenuse squared. And then we take the square root of both sides, and the hypotenuse is equal to plus or minus 5. Now the hypotenuses are always going to be positive. We're going to treat that like a distance, which is always positive, or a radius. Again, always positive in a circle. So now my sine of theta is the opposite over hypotenuse. So the opposite is 4, the hypotenuse is 5, and here's your answer. And the answer was as quick and easy if and only if you drew a right triangle. So now let's level up a little bit. That was kind of like level 1, easy level. Now let's go to a slightly more challenging level. Let's go to the cosine of the inverse sine of negative 40/41. So what we're going to do is we're going to boil this down to some theta. So if we find cosine theta, which is adjacent over hypotenuse, of some triangle in relationship to theta, then what we can do is we can have our answer. So we're looking at an inverse sine, which exists either in the first or fourth quadrant. These are the restrictions of an inverse function. So, inverse sine. So it looks like the value inside that parentheses is negative. So we must be in the fourth quadrant. We have to be in the fourth quadrant because this was negative. Can't be in the first quadrant if you have this problem. So let's again use the relationship of sine, and that's going to be opposite over hypotenuse. And the opposite side here would then be negative 40, because it is a y value, and y values are negative, okay? And then here, this hypotenuse is 41. So negative 40 over 41. So it's time to find our missing side, x. So let's get out our Pythagorean theorem, which is x squared plus y squared equals hypotenuse squared. And so we don't know the x in this case, but we do know the y, which is negative 40. Using the negative here is going to help. And then I have my hypotenuse squared. Oh, but I know my hypotenuse in this case. Nice. My hypotenuse in this case is 41. So x squared. Now I take my negative 40 times negative 40, and that gives me 1600. This answer is not going to be as ugly as you think it is, because 41 times 41 is 1681. And if I use my inverse operation to simplify that, x squared is equal to 81, and then we take the square root of both sides. X is equal to plus or minus 9. Oh, I wrote plus or minus twice. Okay. X is equal to plus or minus 9. And in this case, it would be plus because x is positive in the in the first or the fourth quadrant. So now that we know that my right triangle is negative 40 and 41, the adjacent over hypotenuse is going to be 9 41ths or 41sts. And that's your answer. That is your answer right there. Okay, problem 26. Woof, this is going to be a lot tougher because the last two problems that we just dealt with were right triangles that had perfect Pythagorean triples. This one ain't it. This is a negative 1/3, and this means I'm going to be drawing a triangle here in the second quadrant, because cosine is going to be either the second quadrant or the first quadrant, and my cosine value is definitely negative, so here I go. I have now drawn a triangle in the second quadrant as a reference angle to the x-axis. This is how you have to draw your triangles. Look back at all three of these triangles that you just drew. They were all drawn with reference to the x-axis. And there's nothing going to be drawn in the third quadrant, since inverses actually we don't play with inverses in the third quadrant. It's either the first and fourth for sine and tangent, or it's the first and second for inverse cosine. All right, now cosine. Cosine is the adjacent over hypotenuse. So the adjacent side is negative 1. That makes sense since we are negative x. And the hypotenuse is 3. Well, it's time to play Pythagorean theorem. So what we have is now x squared plus y squared equals hypotenuse squared. The x is negative 1. The y is unknown. And the hypotenuse is 3. Negative 1 squared is 1. Y squared is just y squared. And 3 squared is 9. Subtract 1 from both sides. That inverse operation simplifies the 1's and gives me y squared is equal to 8. Then we take the square root of both sides, and this is where things get a little tricky. Y is equal to plus or minus the square root of 8. Now, in this case, we're going to take the positive value, but the square root of 8 can be broken into the square root of 4 and the square root of 2, because the square root of 8 is a perfect square. It's a product of a perfect square and a non-perfect square. So this makes 2 square root of 2, so y is equal to the positive 2 square root of 2. There we go. That is your answer for the missing value of y. So now what we need is, since this is essentially a representation of theta, if we find the cotangent of theta, we should be able to figure out our answer. Now the cotangent of theta is the reciprocal relationship of tangent. Tangent is opposite over adjacent, so adjacent over opposite is our cotangent. Now, if you're feeling like, oh, we're going to be done with this problem in a hot second, I hate to burst your bubble there, because the cotangent of theta of this relationship is going to be the adjacent side, -1, over the opposite side, which is 2 square roots of 2, and we can't leave our answer like that because we can't leave a radical in the denominator. So what I'm going to do is I'm going to take that -1 and 2 square root of 2, I'm going to multiply by 1. Now this 1 looks like a rectangle, but that means I'm going to make it square root of 2 over square root of 2, and that then converts the numerator into negative square root of 2 and the denominator into 2 square root of 4, which is the same thing as 2 times 2, which is -2 over 4. This is your final answer for the cotangent of theta. So what did this problem do to kind of really push you in comparison to the last two? Well, it made you remember your radicals and your proper simplification. And that, my friends, is the end of this section, and it's the end of the session. And I thank you for tagging along with me on a very in-depth look at the inverse trigonometric functions, which are going to be critical in the next unit when we start to look at solving for theta in within a confined domain for our functions. So thanks again for watching.